In this session here, we're going to take a look at linear functions. Session 14 looked at the direct variation, and what we're going to see is the direct variation is also a linear function. It's just a special type of a linear function. Now we're just going to deal with the overall category called linear functions. In order to illustrate this, take a look at a short word problem here. A team of hikers drive up to a small village in the mountains, which is about 1 kilometer or kilometer above sea level. The village is. From there, they plan on hiking up the mountains at a rate of 2 kilometers per day above sea level. This right here, this word problem, can be solved and can be represented as a function. Now, in this particular function, I'm going to have y represent the height above sea level that the hikers are at. And on the x-axis, what we're going to have it represent are the number of days that the hikers spent hiking up the mountains. So let's see if we can write a formula, a function for this particular, or a formula equation for this particular function here. Let's go ahead and start it off with y, the letter y. If you remember, our direct variation is in the format of y equals ax. Well, here, y is going to represent our height above sea level in kilometers. We're going to go ahead and write a constant of 2 because at the end of each day, they're going to go up 2 kilometers above sea level. So x represents the number of days. So at the end of the first day here, if x is 1, how many kilometers above sea level did they climb that day? Well, they would have climbed 2. 2 times 1. However, they're not starting at 0 kilometers. They're not starting at sea level here. They're starting at 1 kilometer above sea level. They're driving up to the small village. They don't start hiking until they get up to the village itself, which is 1 kilometer above sea level. So at 0 days of hiking, how far above sea level are they? Well, assuming that they've completed their drive, after 0 days of hiking, they're 1 kilometer above sea level. So what we can do is we can add this 1 here. In this particular example, you just kind of look at it as the starting point. A head start if you want to look at it that way, but the starting point. They're not going to start their hike until they drive up to the village that's 1 kilometer above sea level. So the actual formula for this particular function that we're going to be graphing here is y equals 2x plus 1. And once again, y equaling the height above sea level, x equaling the number of days that they have spent hiking. So then, here we have the same formula, y equals 2x plus 1, and I went ahead and plotted out on a table here 4 points. 4 different time periods. Remember x equals days, y equals the height in kilometers. After 0 days of hiking, how far are the hikers above sea level? Well, they're 1 kilometer above sea level because that's the height above sea level of the village, which is where they begin their hike from. That takes care of that one. Next, after they leave the village, they hike for 1 entire day or 1 full day. At the end of that 1 day, how many kilometers above sea level are they now? Well, if we stuck this 1 back into our formula here for an x, 2 times 1 would be 2, plus 1 would be 3. Y would equal 3. So we come down here to our origin, come over 1 on the x, and up 3 on the y. So there's our second point. After the end of day 1, they are now 3 kilometers above sea level. At the end of day 2, how many kilometers above sea level are they? Well, we take that 2 for x, stick it back into the formula. 2 times 2 is 4, plus 1 is 5. So at the end of 2 days, they are now 5 kilometers above sea level. Come to our origin, come over 2 for the x's, and then up 5 for the y's. That takes care of our third point there. And then we'll just take a look at one more. At the end of 3 days, how many kilometers above sea level are they now? We'll stick the 3 into our formula. 3 times 2 is 6, plus the 1 is 7. So at the end of the third day, 1, 2, 3 for our x's. They are now 7 kilometers above sea level. We're going to go ahead and stop it there. So right here now is the plot of those 4 points representing where they were at the end of each of the 4 days. If you can take a look visually, once again we're using graph paper that has some equally spaced lining, so we can kind of depend upon our eyes here. Is this going to be a curve or is it going to be a straight line when we connect these 4 points? It's going to be a straight line. So I'm going to go here and just go ahead and connect those. There's our straight line. That is a linear function. A linear function is a function whose graph is a straight line. Well, the question then is, how is this any different from a direct variation? In the previous lesson, we took a look at the direct variation, and it also was a straight line. So what's the difference between a direct variation and a linear function? Well, if you remember, a portion of the definition for a direct variation is not only is the graph of it a straight line, but in a direct variation, the line also has to intersect your origin, which is at 0, 0, 0x, 0y. In this particular function here, does it intersect at 0, 0 at the origin? No, it doesn't. That is why this is not a direct variation. It is, however, still a linear function. So we see that a direct variation is just a special type of linear function whereby the graph of the linear function is a straight line that goes through the origin. Here, we're just using the generic or the general description, linear function, which just says that the graph of the function itself will be a straight line. That then takes us to our final review page. We've already gone over the linear function. It's a function whose graph is a straight line. And then lastly, a linear function will have an equation in the form of y equals ax plus b, where both x and y are the variables and both a and b are the constants. Now if we back up quickly, y equals ax plus b, y equals ax plus b. So I'm going to go ahead and just quickly write this here. And then what we're going to do is take a look at the function above it in red. Is this function up here in this format? Well, remember, in a linear function, the y and the x here represent our 2 variables. Well, in this function up here, do both the x's and the y's vary? Well, yes, they do. They change. At one point, x is 0. At another point, x is 1. At another point, it's 2. At one point, the y value is 1. At another one, it's 3. At another one, it's 5. So you can see that the values for x and y both vary. However, in a linear function, this a that's being multiplied by the x is a constant, as well as this b that gets added on at the end of the equation. It is also a constant. And what does that mean? It just means that within the formula itself, within the equation itself, does this 2 ever change, or does this 1 ever change to a different number? No, they remain constant within the equation itself. It's only the x and the y that change. Those are our variables. Okay then, that'll finish up session 16 on linear functions.